Talking about types of reactions, and last time we really talked about one sort of big classification of reactions, which were double displacement reactions. Remember, a double displacement reaction is, you could think of it sort of as the big umbrella of classification. The way you could always recognize it, like we saw in that experiment as well, is you will always have really a combination of two sort of ionic compounds, sort of the only reaction where that occurs, that you're starting out with those guys. And always when you have that situation, this is always what's going to happen is basically the two positive guys are again just going to kind of switch partners. And you'll make new ionic compounds on the other side of the arrow. And as we talked about last time, and as we saw in the sort of that experiment, in certain situations, the result of those ion switching partners will result in a solid being formed or a precipitate. And that is a more specific type of double displacement reaction, which is known as a precipitation reaction. And that's a more specific type of classification of a double displacement reaction. Another situation that can occur is a lot of times in an acid-base reaction, upon that switch, one of these guys will make water, and that typically will occur in those acid-base reactions or acid-base neutralization reactions. And you will make that water, and that is essentially what is happening. And the double displacement reaction really accounts for, as we talked about, two of the three reasons why reactions take place. It accounts for a solid being formed, it accounts for water being formed, and these are the reactions that do that. When we do have a double displacement reaction, we also can, as we talked about, write three types of equations. Let's go underneath here, NaNO3. And this is the molecular equation. And it's the equation that we normally just write out with the proper formulas, just like we're doing nomenclature, get all the proper formulas down. We could also write a total ionic equation where anything that's a strong electrolyte, which a lot of ionic things are, will break apart into their ions. Let's go underneath. We do keep together anything that is a solid, anything that is a liquid, anything that is a weak electrolyte will typically be kept together. And this again is the total ionic equation, or again, sometimes the complete ionic equation. Remember, from the total ionic equation, we can find our spectator ions, which once again are ions that look exactly the same, and you have the exact same amount of those ions on both sides of the arrow. Those are our spectator ions, which means they are just watching. And we typically cancel those out. That gives us our third type of equation, which is sometimes a really important equation, which is known as the net ionic equation. And net ionic equation basically will tell you pretty much in that particular reaction what is actually occurring to make the product that you made. And in this particular example here, it is the silver ion from the silver nitrate finding the chloride ion from the sodium chloride that's going to come together and make a solid. It makes a solid based on what we also saw the other day, which is solubility rules. And we can use solubility rules to help us decide when we put two ions together. Thank you. Here's good things. When we put two ions together, will we get a solid that would form, which means it's insoluble? Will we get a solution that will form, which means that it is soluble? Any questions on any of that stuff from last time? All right. So, as I'd mentioned before, three reasons why a reaction takes place: solid being formed, water being formed, and the third reason is basically from another type of classification of reactions, which are redox reactions. And redox reactions, again, are basically oxidation reduction reactions. And these involve a transfer of electrons, which again is really the third reason why a reaction takes place. These guys, again, are sometimes just referred to as redox reactions. As we mentioned a little earlier, and as we will see again, oxidation means that typically someone loses electrons. Reduction means someone will gain electrons. And when you lose electrons, you do become more positive. And that again is because you have more protons than electrons. When you gain electrons, you become more negative because you've now gained more negatively charged electrons than, say, protons you started with. And that's one way, as I might have mentioned last time, that you can sort of easily figure out what is being oxidized and what is being reduced. You can kind of just use a basic sort of number line. And if you look at that element, for example, on the left-hand side of the arrow in the equation and compare it to that same element on the right-hand side of the equation, and if you see that their oxidation state or their charge is becoming more positive or at least moving in that direction, then that thing is going through oxidation. And if you do the same thing, you look at the element on the left-hand side of the arrow and compare it to the same element on the right-hand side of the arrow, and you see its charge kind of becoming more negative, that thing is going through reduction. They always occur together, which means one of the nice things about redox reactions is if you could just figure out one of those things, what is being oxidized or what is being reduced, by default, the opposite thing is happening to the other guy that's the reactant. So if you can just figure out one, by default, other thing is happening to the other situation. So for example, if you had a reaction where you had, say, iron 3 chloride to iron 2 chloride here, and we look at really the charges on each side here. This is again -1 because it's chloride. There's 3 of them. This is again +3 on the left-hand side of the iron. Over here, this is again -1 for the chloride. There's 2 of them. It is +2. So what is happening when we look at the iron in this particular case is the iron is starting at +3, which would be over here, and it's ending at +2, which means it's actually going towards the negative side. And it is the iron here that is actually going through reduction. And again, that is how you can sort of use that number line to sort of figure out, what is being reduced and what is being oxidized. In this particular case, the chloride, there's nothing happening with the chloride. It's -1 on both sides, so it's not being reduced or oxidized. In this example, there would be something else there probably reacting that would be going through oxidation. But in this case, the chloride is actually more of a spectator ion, actually, in this particular case. Yeah. Was that? Yeah, I don't know. So this is just like a half of the equation. There's other things there. But in case if you look at the chloride itself, on the left-hand side, the chloride is actually still -1 in terms of its oxidation state, and it's still -1 on the other side. So it is nothing's happening in terms of it losing or gaining electrons. It's actually the same. That's on both sides. Yeah. And this is obviously would be just half of the reaction. There would be something else there on the other side. All right. So yeah. It doesn't. It just happens to do if this was opposite, if you started with something that had iron 2 on this side and went to iron 3, then the opposite thing would be happening in this case, right? Because in this case, the iron would start at 2 and end up at 3. So in this case, this would be going through oxidation. So it just kind of depends on the situation as to what the charges are of those elements on each side of the arrow as to what's happening. And again, like I said, this would be like only half of the overall reaction of what's just looking at iron in this particular example. All right. So let's take a look here. We have sodium chloride being formed in this particular case. And once again, if we just look at this reaction and really sort of, it's really the oxidation states is what we're looking at. But we could kind of, for this class, consider it kind of like the charges, even though they're not always the same. Remember that if you have any element from the periodic table that is by itself, It is not combined with anything else, and it's just naturally how it comes by itself. They really don't have any charges. So the sodium over here is 0. Chlorine, again, is naturally how it comes as a diatomic molecule. So both of those guys are kind of starting out with 0 in terms of their oxidation state or their charge. And when they do hook up on the right-hand side, these guys are ions in this case, right? Sodium chloride is an ionic compound. And once again, sodium is group 1, which means it has a +1 charge. The chloride here is -1, which means group 7, which is -1 in this case. And again, if we kind of look at what is going on in this situation, if we look at the sodium here is starting at 0. And on the right-hand side, the sodium is ending at +1. It is moving in the positive direction, which means here the sodium is going through oxidation. Now, once I identify that sodium is going through oxidation, I really don't have to do anything with the other guy because by default, this guy is going to be going through reduction. So as long as you can kind of identify one of them, you'll know what's happening to the other. We could still use the number line for the chloride as well. Again, the chlorine is starting at 0 and it's ending at -1, which means it's becoming more negative as it goes from left to right, and that means it is going through reduction. So this is a redox reaction, and what is actually happening here is the sodium is sending an electron over to the chlorine in this case, and that is how it's becoming negatively 1 charge. That is the transfer of electron that is happening in this case, and that is why this is considered a redox reaction, and this is ultimately what is happening here. As I think I mentioned last time, in those double displacement reactions that we've talked about, precipitation reactions, acid-base reactions, there is no transfer of electrons happening in those reactions. Everybody remains the same charges on both sides. So just to illustrate that, we go back and take a look at that example. That was like silver nitrate plus our sodium chloride going to silver chloride and sodium nitrate. If we just look at the oxidation states or charges, everybody on each side, that is +1, the nitrate's -1. That is +1, the chloride's -1. That is still +1, chloride's -1. That is +1, and nitrate is -1. Absolutely no change in the oxidation states or anything like that, or the charges for each of these elements on both sides. So there is no electrons being transferred in this case or accepted in this case. So again, in double displacement reactions, we don't have that transfer of electrons that is occurring. Everybody maintains their same sort of charges. No transfer of electrons here. And that is completely different from what we're looking at here, where basically that's everything that's happening is really ultimately electrons being transferred from one place to the next. That's why the sodium goes from no charge to positively charged, because it lost an electron, now it has more protons, becomes positively charged. For our chlorine, it has no charge, gains an electron, becomes negatively 1 charge because it gained an extra negative electron. And that is how the ionic compound then comes together, right? Now we got things with charges, they're going to be attracted to each other, and they're going to come together. Any questions on that there? Now, the good news about some of these redox reactions is when you have a situation like this, this is also something we've talked about before. Sodium is a metal, chlorine is a non-metal, and that always is going to form an ionic compound. And we know in an ionic compound, which one usually gives away the electrons? It is the metals, right? Because they usually become positively charged, right? And our non-metals usually become negatively charged. So whenever you have a metal and a non-metal coming together like we do in this sort of reaction, the metal should always be the one being oxidized because it should always be the one giving away the electrons. The non-metal should always be accepting those electrons and gaining them, and they should always be the one being reduced. So if you're dealing with like metal and non-metal together, it's really simple to sort of figure out which one's being oxidized and reduced because, again, the metal should always be oxidized. But when you got a couple of metals involved in the reactants, then again, you can kind of look at the charges and that oxidation state. So as I mentioned before, this again is what is referred to as a redox reaction or an oxidation reduction reaction. We have electrons being transferred. Here's another example of a redox reaction. That is magnesium by itself, no charge. That is naturally the way oxygen comes, no charge. We take a look at the magnesium over here. This is an ionic compound. Magnesium is group 2 plus 2, oxygen group 6. Once again, if you roll with a little number line action, magnesium here starting at 0, ending at plus 2, becoming more positive. So again here, this is going through oxidation. And oxygen starting at 0 and ending at minus 2 on the other side, and it's becoming more negative, and this guy is going through reduction. So again, this is a redox reaction that's happening, same deal. Magnesium is sending the electrons over to the oxygen in this case, and it's accepting it. Same deal as I just mentioned a second ago. Magnesium's a metal, oxygen's a non-metal, so we should know magnesium should lose the electrons and get oxidized, and oxygen being the non-metal should gain the electrons and being reduced. So again, if you got that situation, ionic compound, this should always be the case in this case. You can, for example, write a couple of types of reactions to illustrate what is going on. So in this particular case, we got some magnesium going to 2 magnesiums plus 4 electrons here. This is what is sometimes referred to as a oxidation half reaction. And it is half of what is going on in this case. And in this case, we know it's an oxidation half reaction because the electrons are on the product side. So if you see a reaction written like this with electrons on the product side, that means they're losing them, they're giving them off, and that usually indicates a oxidation half reaction. You could also write a half reaction for the reduction, which in this case looks like this. And this is what is known as the reduction half reaction. And it's a reduction half reaction because electrons are on the reactant side and they're like being gained by the reactant in that case. Why are they called half reactions? Because frankly, they're half of what is going on in the overall reaction. And if you add both of those reactions back together, you get the overall reaction that's taking place. And you'll learn more about that in 1A and 1B as well when you balance some redox reactions fully. But they're called half reactions because they display half of what is going on there. Magnesium losing the electrons and oxygen gaining electrons. What you also see in reactions is the number of electrons are the same because electrons that are lost in this example by magnesium is the same number of electrons that's gained by oxygen. By the way, there are 4 electrons lost by magnesium. That is because magnesium loses 2 electrons. That's how you become positive 2. There are 2 of magnesium in this equation. So that's why there's 4 total electrons that are being lost, 2 from each magnesium. And oxygen is gaining 4 electrons because oxygen ends up with a minus 2 charge, which means it's gained 2 electrons, and there's 2 oxygens in the second reaction. So again, that's why there's a total of 4 electrons happening here. Any questions on that there? And here again, there's oxygen. And again, that's how you could recognize it. Like I said just a second ago, electrons on the product side, definitely oxidation. Electrons on the reactant side, reduction, gaining. And as you can see there, if you add them together, the electrons will cancel since they're on opposite sides of the arrow and exactly the same. Everybody on the left-hand side stays there, and everybody on the right-hand side of the arrow stays there. And that's back to the overall reaction. Basically, these guys come together to make that, and then these guys come together down here. Now, for us, that's pretty much all we're going to kind of look at in terms of oxidation and reduction is And most of the time in general chemistry, you look at sort of electrons being gained and lost. There are some other definitions of oxidation and reduction that if you continue on with chemistry, that you will see when you get to organic chemistry. Sometimes in organic chemistry, there's not a lot of metals involved. So there's a lot of non-metals involved. So sometimes in organic chemistry, for example, we don't look at just electrons, but for oxidation, it can mean you lose electrons. Also mean that you gain oxygen as you go from reactants to products, or you lose hydrogen as you go from reactants to products. Again, these two are probably definitions you'll see more in organic chemistry than in general chemistry. And reduction has the similar definitions. You can gain electrons, you can lose oxygen as you go from reactants to products, and you could gain hydrogen as you go from reactants to products. So those are three really definitions of each of those. And just to illustrate this here, if we take a look at it, we can see that as we go from our sulfur here, it had 2 oxygens to begin with. Sulfur ends up with 3 oxygens. It has gained oxygen, which means this is going through oxidation. And by default, this is going through reduction. So that is sometimes what you would be looking at in this particular case, hydrogen or oxygen. Since we don't really assign oxidation numbers or states really in this class, just to illustrate something you'll learn in later general chemistry, the actual oxidation state of the sulfur on the left-hand side here is oxygen is -2. That gives you a -4 total. So the sulfur here is actually rocking a +4 oxidation state, which is, again, a little bit different than the charge. And if you come over here to this side, oxygen is -2, that's -6. So the sulfur here on this side actually has a +6 oxidation state. And if you follow that sort of number line deal like we just talked about, the sulfur on the left-hand side is +4, ends up at +6 on their side, becoming more positive, and is going through oxidation. So you may be asking yourself, and again, we're not going to get too deep into this, but isn't sulfur -2 on the periodic table? And it is in an ionic compound where electrons are completely transferred. But in these cases here, these guys are actually sharing electrons. And because they are sharing electrons, in the case of this guy is sharing electrons with 2 oxygens to begin with. Oxygen is more electronegative, which means because they're sharing electrons, the electrons are going to be heading towards the oxygen in this case, making the sulfur more positive here because they're sharing electrons. Not as positive as on this side, where the sulfur is hooked up to not 2 but 3 oxygens, which is going to pull the electrons further towards all those oxygens, making the sulfur more and more negative, more and more positive in this case. And that's how it ends up with a +6 charge in that situation, because there's more electrons moving away from the sulfur. So oxidation state, like I said earlier, is a little bit different than the charge we associate with elements in an ionic compound because they're sharing electrons, and electronegativity has to do with that. Yes? It has a -2 charge for some other reasons, but because of the way that they're sharing electrons, um, the oxygens in that and also the sulfur take on a certain what is known as a formal charge. And for example, in that sort of arrangement, if you did like oxygen just all single bond, or sulfate all single bonded, for example, in this case, if you calculate what's known as formal charge, which is sort of what each of these elements charge would be if like all the electrons were transferred, the sulfur in the middle actually has a +4 charge, and each of the oxygens have a -1 charge. So overall there, I'm sorry, that's a what did I say there? +2 charge, not +4 in the middle. Bad. that has a +2 charge in the middle, and all the other ones are -1s. So that's -4, and +2 is a -2 overall charge when you take all those, what's referred to as formal charge, into account. And that's where the charge comes from for this polyatomic. Same thing with that, yeah. And it's really what's known as formal charge, and it has to do similar to this as well as sort of how the electrons are sort of being shared in that situation based on electronegativity and sort of the charges that each of those elements sort of take on through the sharing of electrons. Other questions? Okay. All right, so as we've been talking about, these are the three main reasons why reactions take place. And we talked about, obviously, last time, our double displacement reactions, which, again, take care of two of the three reasons, and our redox reactions for this one. So just to review a couple of those, again, double displacement reactions. We saw precipitation reactions, which, again, is a double displacement reaction. And again, that is a positive, negative, positive, negative. And once again, in this situation, there is no electrons being transferred, and we're just getting that switch of partners like we talked about last time. And obviously here we do form a solid. So as we talked about last time, a more specific classification of double displacement is a precipitation reaction, which occurs when a solid is formed by that double exchange. And again, that is always how you could recognize it, by two ionic compounds coming together. No other reaction will have that sort of setup. We also saw earlier the acid-base reaction here, where ultimately it is still a double displacement reaction. And again, we're going to switch partners here. And that is what's going to form our water and our salt. If you remember in this case, right, we form water and a salt, which is an ionic compound. And again, this is a double displacement reaction. And a more specific classification, as we talked about, is sometimes referred to as acid-base neutralization reactions, because again, water is mainly what is formed in this case. All right, so now we're going to talk about some more specific ways to classify redox reactions. So these are involving electrons being transferred. So if we take a look at this guy here, once again, lithium is 0, fluorine is 0. When they come together on the other side, +1 for the lithium, -1 for the fluoride. And if you take a look, lithium starting at 0, ending at +1, becoming more positive, going through oxidation. And fluorine here going through reduction as it goes from 0 to -1, becoming more negative in this case. So this is definitely a redox reaction where, once again, our metal is sending the electrons over to the fluorine in this case. And this reaction here, if we look at it, is what is known as a single replacement reaction. A single replacement reaction is a more specific classification of a double displacement reaction. And what is happening here is the zinc is coming in and kicking out the hydrogen. When it does so, hydrogen will come off as hydrogen gas. You'll see some bubbles happening in your test tube, and you'll make some zinc chloride. This is still a redox reaction that is happening. Zinc has no charge on this side. Hydrochloric acid +1 for the hydrogen, bless you, -1 for the chlorine. Hydrogen on the other side, gas, is how it naturally comes, no oxidation state. Zinc is an ionic compound, which means it's +2, and chloride is -1 in this case. So if you look at the little number line here to see what is going on, the zinc on the left-hand side is 0, ends up on the right-hand side as +2, becoming more positive. It is the zinc that is going through oxidation here. The hydrogen in this case on the left-hand side is +1. And on the right-hand side, it is 0. So it is heading in the more negative direction. It is actually the hydrogen here that is being reduced in this case, or going through reduction. So we have electrons being transferred from the zinc to the hydrogen in this case, and that is what is actually going on in this reaction. Is there anything happening with the chlorine in this case on each side? No, it's exactly the same charge, so there's no electrons actually happening in this case. Now, you can, if you wanted to, take this reaction, and you could write the same type of equation that we saw with double displacement reactions, which is our molecular equation, total ionic equation, and net ionic equation. So if we look at that here for this reaction, and we take our molecular equation that was given to us, which was the zinc plus the hydrochloric acid, making our H2 and our zinc chloride here. Put a 2 there as well. So we can break this up into a total ionic equation. Since zinc is a solid, obviously we keep it together. Hydrochloric acid is a strong acid, which means it's a strong electrolyte. It will break apart into 2 H pluses and 2 chlorides. H2 is a gas, which means it will stay together. And the zinc chloride will break apart into zinc with a +2 charge and 2 chlorides in this case. This is our total ionic equation. This means in this reaction, the spectator ion is actually just the chloride, which is why nothing is happening to it. There's actually just one spectator ion in this case. And just like we did on the other one, we would cancel that out. And this gives us our net ionic equation of what is really happening in this case, which is the zinc plus the couple of H pluses that are floating around in the solution. We'll do a little electron transfer. Oops. And the zinc's going to send those electrons over to our hydrogens. There are 2 hydrogens. Each is going to gain 1 electron. And that's going to make H2 on the other side, and that's the bubbles. So this is ultimately what is happening in this reaction, and you could also do a net ionic equation for this type of reaction as well, and it illustrates, again, what is actually taking place. Any questions on that there? So ultimately what is happening here, like I mentioned, the zinc has given up its electrons. It is the H pluses that are floating around are going to accept them. They're willing to accept them because, frankly, they're positively charged, which means they're electron deficient, and they're going to be happy to kind of pick up those electrons and become hydrogen gas. And if you did this, like I said, all that H plus that was floating around in the solution would then make hydrogen gas, and you would see all those bubbles, which I think we've done probably in one of those experiments where we put zinc in hydrochloric acid, and those bubbles are now the hydrogens leaving the solution as hydrogen gas, basically, as it bubbles out. Any questions on that there? We actually have seen, and it does have this general setup of A plus BC, and then in a single replacement reaction, this is the only time you will have this sort of setup where you will have something that has no charge, which can be a metal, and something that's an ionic compound. So whenever you have that setup, this is going to be a single replacement reaction. And because the metal here doesn't have a charge, but when they do gain a charge, they become positively charged, it will come in and kick out the positive guy here. And it will make a new ionic compound at that point. And whatever gets kicked out will end up by itself with no charge. We have actually seen these reactions when we did those halogens and the different layers, and when they were switching colors, the top layer color was switching, because you could have this reaction where this guy again is 0 and an ionic compound, but this could be a nonmetal. And what happens in this case is nonmetals normally become negatively charged. It will kick out the negative guy in this case and make a new ionic compound. And what comes out will be 0. If you remember when we did that experiment with the different layers and the halogens, it went from like yellow to orange or orange to purple. In order for this reaction to actually take place, whatever is coming in needs to be more reactive than what is replacing. So in this case, A needs to be more reactive than what it is replacing. And if A is not more reactive, then you will not get a reaction take place. If it is, you will get a reaction take place. So for example, if we take this equation up here that we just looked at with the zinc and the hydrochloric acid, but you decide, I don't want to do it with zinc, I want to actually do it with like copper metal. I'm going to do copper metal, which you might have done as well. I almost think you did in one of those reactions. You will actually get no reaction take place, and that is because when copper tries to come in and kick out the hydrogen, copper is less reactive than hydrogen, and that reaction will not take place. So not all single replacement reactions will actually occur if that guy coming in is less reactive than what happens. We also saw that with the halogens, right? Iodine could not replace anybody. So when iodine was trying to come in, it would not replace chlorine. It would not replace bromine because it was less reactive. Remember, those basically just stayed purple up there in the top layer and then it changed color. How do you know if this reaction is going to take place? There is something that is known as an activity series. And basically, a basic activity series is really just a list of elements, usually hydrogen somewhere there in the middle. And basically, anything higher on the list will replace anybody lower on the list, and anybody lower on the list will not replace anybody higher on the list. So if you were to look at the relationship here, zinc would be higher on the list, and that reaction would take place because it's more reactive. Copper would be lower than hydrogen, and that reaction would not take place. So you'll sometimes come across an activity series and a basic one. That's pretty much how you use it. Higher, more reactive than anything lower on the list. And anything higher on the list should replace anybody lower on the list. All right, so redox reaction, single replacement is one type of redox reaction. Another type of redox reaction is a combustion reaction. So this again is a redox reaction. And I would say probably 9 times out of 10, maybe more, when you talk about a combustion reaction with your friends, I don't know why you're doing that. You're probably going to be talking about the organic combustion reaction is what most people do. And that is usually an organic guy plus some oxygen makes CO2 and water. Those are usually an organic combustion reaction. As you can see here, like when you light your Bunsen burner, oxygen and methane, CO2 and water is formed. And an organic guy is usually carbon, hydrogen, maybe oxygen involved. Same thing down here, carbon, hydrogen, oxygen, CO2 and water. That is basically your classic combustion reaction. To be truthfully honest with you, the only thing that you really need for a reaction to be classified as a combustion reaction is simply O2. So technically speaking, if you got O2 on the left-hand side, that is enough for it to be classified as a combustion reaction. But like I said before, most people would probably classify combustion reaction more so in the organic version there as well. And again, this is still a redox reaction that's happening. Just to give you just an idea of a quick one here, oxygen is 0. Over here it's -2. And again, oxygen is going from 0 to -2, becoming more negative. So it is going through reduction in this case as well. You could also see the carbon gained oxygen from left to right, right? Carbon, no oxygen. On the right-hand side has oxygen. Another definition of oxidation. So carbon is going through oxidation in this case as well. So these are combustion reactions, and they are under the classification of redox reactions happening. Another more specific classification of a redox reaction is a synthesis or combination reaction. And once again here, the way you can recognize this is pretty straightforward. It is typically 2 things make one thing. Like you're putting it together, you're comboing it together. So if you look here, formation of water, two things make one thing. Sodium chloride, two things make one thing, right? So those are all synthesis and combination reactions. There are also still redox reactions that are occurring. If you look at the hydrogen over here, that is 0. Oxygen is 0. Hydrogen on the right-hand side +1. Oxygen on the left-hand side -2. Hydrogen, once again, is going from 0 in this case to +1 and becoming more positive, is being oxidized. Oxygen is going from 0 to -2, becoming more negative. It is being reduced in this case. So again, this is really electrons being transferred. It's a redox reaction that is happening. So when you have two things that make one thing, that is a synthesis or combination. This also maybe brings up a point that maybe you have recognized here, which is there are many different ways you could classify a reaction. You could look at one reaction, and there's actually several different sort of classifications you could do. So if we take a look at this one here that we just saw on the previous slide, put 2 there to balance it, put 2 there. This is definitely two things that make one. So this is a synthesis reaction. This is also a redox reaction, as we talked about previously, right? Electrons being transferred. So you could classify this as a redox reaction. And dare I say, this also has oxygen in it. You could classify this as a combustion reaction. So this one reaction can actually be classified in some different ways, depending on what you're looking at. I would say probably most people would most likely classify this as a synthesis or combination reaction or a combustion reaction, but most would probably go synthesis or combination. But you could definitely classify the same reaction in multiple ways. Just like we saw with double displacement reactions, we could call it a precipitation reaction. A precipitation reaction, it is also a double displacement reaction that's happening. So there are different ways that you could classify the same reaction, again, depending on sort of what you're looking at. So synthesis is putting it together. The sort of opposite of that reaction is a decomposition reaction, and that is breaking it apart. So the way you can recognize a decomposition reaction is you start with one thing and you make a couple or more. So it's really the opposite reaction that occurs. You could do that if you run an electrical current across water and do the electrolysis of water. You could break water into one thing, into two things, and it's a decomposition reaction. It is still a reduction reaction, an oxidation reaction. Hydrogen +1, -2, 0, and 0. In this particular case, going in the opposite direction, the hydrogen is going from +1 to 0. It's actually getting reduced in this case. And the oxygen is going from -2 to 0, which means it's getting oxidized in this case. It's the opposite of putting it together. So that makes sense because opposite things are happening to break it apart in this case. So decomposition, one thing makes multiple things. Very common thing is if you make some carbonic acid, it very quickly water and CO2, plop, fizz, fizz. Again, one thing making multiple things is a classic decomposition reaction. Question on that there. So just to summarize what we were talking about in terms of classification reactions, we have our double displacement umbrella of reactions, our AB plus BC. Whoops, I'll learn the alphabet, CD. Oops. And in this case, under here, we have more specific classifications, which is a precipitation reaction and an acid-base reaction. And as we talked about, this makes our solid. This makes our water, basically. Now, no electrons being transferred here. On the other side, we have redox reactions, which is all about electrons being transferred. And more specific classifications of redox reactions is our synthesis, our combination, which is two things make one, our decomposition reaction, which is one thing makes two, our single replacement reaction, which is a thing by itself and an ionic compound coming in and kicking out. And lastly, our combustion reaction, which again, basically, oxygen in general are an organic plus oxygen, CO2 plus water. So those again are big umbrellas of classifications, double displacement and redox. And as we talked about, under each of those, you could have a, again, more specific way of classifying these reactions based on what is going on. Any questions on ways to classify reactions? All right, that wraps up chapter 7. We're going to go off to chapter 9 next. And just find it here. Okay, so in this reaction, or in this chapter, we're going to talk about really kind of putting together a few of the last chapters that we've talked about in terms of calculations and equations. And in this chapter, we're going to talk about how you're going to do what is known as stoichiometry, which are calculations that are from an equation. They will involve, obviously, balancing equations, which is chapter 6. They will also involve from chapter 8, where we talked about grams and moles and converting things to moles. So in this, definitely, we will be using from chapter 6 our balancing equations and our grams to moles, or our moles to grams. Remember, as we talked about, that is our molar mass conversion from the periodic table that we can use to do that conversion. And that's a very common conversion that is used in this chapter. And definitely you should always, as we'll talk about, make sure that your equation is balanced. So chapter 6, again, make sure you've watched chapter 6 if you haven't, and make sure you understand how to properly balance equations. So when we look at a balanced equation, there are a couple of ways that we can sort of look at the balanced equation and interpret it. One way is we could look at the coefficients, and in this particular case, we could use this relationship here, which is we could say there are two molecules of H2 react with one molecule of O2 to form two molecules of H2O. Now, the relationship that we really use the most in stoichiometry and in this chapter is this relationship here. And it is sometimes referred to as the mole-to-mole relationship. And it also comes from the coefficients from the balanced equation. This again is why when you're doing these type of problems, first thing you always do is make sure your equation is balanced, because if you do not have a balanced equation, you are going to have the wrong relationship and your calculation is going to be doomed from the beginning. So again, it comes from the coefficients. So there's a 2 in front of H2. We could say that is 2 moles of H2 react with 1 mole of O2 to make us 2 moles of H2O. The last one there is the conservation of mass, because we don't lose any elements in a chemical reaction. If we have 2 hydrogens on the left, or 4 on the left, we'll have 4 hydrogens on the right. They both have the same mass of 1.008 each. And same thing with the oxygen. We got 2 on the left and 2 on the right. And again, they both have a mass of 16. So we have the conservation of mass of each of the elements involved in this chemical reaction. But this is really the mole-to-mole relationship is definitely the one that we use in this chapter and with stoichiometry. So let's talk a little about stoichiometry, and people get really confused about stoichiometry or anxiety, I guess, about stoichiometry. But really, to think of stoichiometry, and really all stoichiometry is it is a conversion factor. And it is just a conversion factor that you're going to use in your calculation. The difference is you're not going to go to like a table or anything like that to look up the conversion factor. You're going to actually look it up in the equation, the balanced equation. And that is because in these type of problems, let's just say we have this reaction here. Maybe we're given information about B in this reaction, but we're actually interested in how much product we're going to make in this reaction. So because the only piece of information we're kind of given is about B, we need some way to go from B in this equation to our product. And that really is what stoichiometry is. We could use that mole to mole relationship from the equation and have a conversion factor. So just from my example here, we could say, oh, there are 2 moles of B, gives you 1 mole of the product in this case. And again, that is the coefficients as to where we get that relationship. So we're able to get a relationship from the balanced equation that allows us to use it as a conversion factor because frankly, all we know in this example is about B, but we're interested in how much product we make. And that's what stoichiometry allows you to do is if you know the balanced equation for the reaction that you're going to do, and you know really just one piece of information, maybe you know how much reactant you started with, or maybe you actually know not what you started with, but how much product you actually made. You could do a calculation to figure out all kinds of things like if I know how much reactants I put into this reaction, I know in theory this is how much product I should get out. This is how much I should make. And that's what stoichiometry could tell you. You could also, like I said, kind of back calculate, which is I made this much product. How much reactants did I start with? So you could do a calculation to figure out how much you started with to make that amount of product. So that's what we use stoichiometry for, to answer those questions of I put in this much reactants, how much product should I produce? Or I produce a certain amount of product, how much reactants I could make. You could also use stoichiometry if you know, say you have a reaction where there's 2 reactants, but you know how much of one reactant you're using. You can use stoichiometry. You got to throw in there with it. Oh, say you got 2 products that you made. Out one product you made, you can use stoichiometry to figure out how much of the other product you should make as well. So it allows much of everybody in the equation you will make or produce or started with, as long as you got kind of one piece of information about what's going on in that reaction. Now, the units that we use for stoichiometry can really be any types of units. Moles and grams are very common, definitely in this chapter. And again, that grams to mole conversion are backwards, used a lot, again, with the molar mass to do that conversion from the periodic table. Later on, when we get into the gas chapter, we may use units of liters, and molarity sometimes is used as well. When we get into sort of concentrations a little bit later on as well. And again, it could really be anything. But mainly in this chapter, probably grams and moles are going to be sort of the units that you'll see the most. We use the mole method, which again is based on the balanced equation. And again, it is just the coefficients. So that is the only things you have to kind of look at. Here are 5 steps to follow in a basic stoichiometry problem. And I would say probably you could reduce this down to 4 steps in most cases. But just in case you were given everything in words and you weren't given an actual equation, but you were told in words of what is reacting or what's happening, you definitely want to make sure you get the right formulas down, as we talked about a little bit ago. You want to make sure you have the right formulas before you do the next thing, which is really important. Balance the equation. Once you balance the equation, you want to take whatever they gave you and basically get it to grams and convert those grams to moles. Then the next step is you want to actually do the mole-to-mole relationship. And lastly, convert moles into some other steps. So basic stoichiometry problems, pretty much these 4 steps. Balance the equation. Get whatever they give you to grams and take those grams to moles. Do the mole to mole relationship from the equation. And then if you do step 3 correctly, you should always be in moles, and you will sometimes have to convert it to some other unit. And I would say very commonly you're going to convert moles on the back end to grams using molar mass, but it could ask you for like pounds or some other weird unit. So you might have to do multiple conversions at the end. Just like a number 2, you may have to do multiple conversions to get it to grams and then grams to moles. But most of the time, you're probably going to go straight from grams to moles, and at the end, moles back to grams, again, using the molar mass is, again, very common way. If you follow these 4 steps for basic stoichiometry problems, it should get you to the answer at the end. All you have to do is keep going forward, don't go backwards. So don't undo things and stuff. So if something is done for you, just go forward on the next step and continue on. So let's take a look at this equation here, and let's talk about really all of the stoichiometry or stoichiometric relationships that we could get from this equation. So the first important thing is we're going to get some relationships or equalities. And they are again going to come from our balanced equation and our coefficients. So from this equation, we could say that for every 2 moles of CO that I put in there, I would also need to put in 1 mole of O2. And again, those are just the coefficients from the balanced equation. Remember, in a balanced equation, if nothing is written in front of a formula, it is assumed to be 1, right? So that is where the 1 comes from. We could also say for every 2 moles of CO I pop in there, I'm going to get out 2 moles of CO2. I could also say for every 1 mole of O2 I put in there, which is here, I could also get out 2 moles of CO2. So from this one equation, we actually have 3 different equalities that we made. And remember, equalities are 2 things that represent on different scales, but represent the same amount of something. So these are all of our equalities that we could get from this equation. And if you remember from chapter 2, from any equality, you could write 2 conversion factors that you could use in a calculation. So in terms of conversion factors here, we could write for our first relationship, for every 2 moles of CO over 1 mole of O2, or we could flip it around like a normal conversion factor, 1 mole of O2, 2 moles of CO. For our second one here, we could write 2 moles of CO over 2 moles of CO2, or we could flip it around, 2 moles of CO2 over 2 moles of CO. And lastly, for the third one there, we could write 1 mole of O2 over 2 moles of CO2, or 2 moles of CO2 over 1 mole of O2. So from this one balanced equation, we actually have available to us 6 different conversion factors that we could use. Will you use all 6 of the problem? The answer is no, because you're definitely doing something wrong if you're using all 6. You will actually only use one of them in a problem. You're going to use the one you need, obviously, in the problem. So available to us, though, are 6 different conversion factors. We will only use one. Now, sometimes people, when we look at the equality on the left-hand side, have a question of 2 does not equal 1, and obviously 2 does not equal 1. Hopefully in math, this still doesn't. And it is not equal to each other in terms of numbers. It is equal to each other in terms of like proportion of how much of each of those you got to toss into that reaction to produce a certain amount of product. So if you were going to make a dozen cookies, You got to put so much eggs in there, right? Flour, chocolate chips, butter, and all that. Certain proportions of each of those to produce like 12 cookies, or you make, or 24 cookies, or however big your cookies are that you're going to be making. And that's what these are. These are really the proportions of each of these that is necessary for this reaction basically to take place. And that really is what stoichiometry is. It's just a conversion factor. And as you can see, where you get it is from that balance equation, which is why the first step in these problems is most important. You should always, always make sure that that equation is balanced. If not, it's just going to throw your calculation off. Any questions on that there? So let's see how we can put these together here just to kind of finish up on a little example of a stoichiometry problem. Let's just say, for example, in this problem, we produced 110 grams of CO2, and we wanted to know how many grams of O2 did we start with. All right, so this is a basic stoichiometry problem. So we want to go through our steps here, and I'm just going to kind of maybe come down that way, maybe. All right. Step number one is we want to balance the equation. So step number one is already done for us. We want to balance the equation, right? Step number two is you're going to take whatever they gave you and convert them to grams and then go from grams to moles. So in my example here, we were given 110 grams of CO2. So we have to convert the 110 grams of CO2 into moles. That's going to require us to go to the periodic table, right? And we're going to find our carbon that says 1201. We're going to find our oxygen that says 16. And we're going to add up the molar mass of CO2, which is 12.01 for our carbon, plus 2 times 16 for our oxygen, and that's going to get us 4401 grams per mole as the molar mass of our CO2. So now that we have our sort of conversion factor for molar mass, we could do our step number two, which is 110 grams of CO2. Opposites cancel, so we want the grams on the bottom. 4401 grams per mole of CO2. And if we got an answer at this point, my calculator turns on. Let's see. We're going to end up with, we'll call it 2.499. I'm not going to round too much right now. 2.499 moles of CO2. So that is your second step, which is whatever piece of information they gave you, you need to get it to grams and then convert grams to moles. Any questions on that so far? The reason we need to do that is if we take a look at the next step, which is the actual stoichiometry step. This is the mole to mole relationship from the equation. Now, the reason we have to do that is if we take a look at what we got going on, in this problem, we're given information about CO2, but we're really not interested in CO2, right? We want to get over to O2, right? So that is where we want to end up. And we need a conversion factor to allow us to do that. So we did it earlier. We could use the balanced equation as a conversion factor, and we could see that for every 1 mole of O2, we get 2 moles of CO2. That gave us an option of 2 conversion factors in this case. Those are our 2 options of conversion factors. Now, we are continuing on with our number from the previous step, which is 2.499 moles of CO2. Remember, that is up on top, and dimensional analysis means opposites cancel. So which conversion factor do I need to use? The one on the left or the one on the right, in this case, to cancel out the CO2? Yeah, I do need to use the one on the left. It has the CO2 in the correct location. Also, you could see I did not use any of the other 5, right? So I just used the one that I needed, and I'm going to do 1 mole of O2 and 2 moles of CO2. This right here, multiplying the top, dividing the bottom, is the big stoichiometry step. So we're going to divide by 2, and that's going to give us 1.2, we'll call it 50 moles of O2. And right there, that comes from the balanced equation. That is the stoichiometry move. At this point, I have now done 3 of the 4 steps. And do I need to do step number 4 here? The answer is I do in this problem. If I was looking for moles as my answer, I could clean up some sig figs and put a box on it and I'd be done at this point, right? But I am looking for grams. And we do have to do the 4th step, which is we're now going to take those moles, in this case, to grams. There is an important piece of this, which is we are no longer talking about CO2, right? So we now need the molar mass of O2, right? Because we've done that conversion. So we have to go back to the periodic table, get the molar mass of O2, 2 times 16 grams per mole gives us 32 grams per mole. And now we can finish out this last step, and I'll just do it right here. Again, we want moles on the bottom, so it cancels, and 32 grams of O2 up on top. And we'll take that and times it by 32, and we'll end up with, we'll call it 40, as in the rounding there, 40.0 grams of O2 in this case. Sig figs based off of the original number of 110, which has 3 significant figures. Those are the 4 basic steps to any stoichiometry problem that's a basic stoichiometry problem. Balance the equation, take what they gave you, the grams, convert those grams to moles, find the 2 things you're interested in the balanced equation and the mole-to-mole relationship, and if needed, take those moles to some other unit, which is grams in this particular example. And again, it could be multiple different units, but usually grams at the back end. Any questions on that? I did it in parts here so you can see all the steps. You could do this all in one calculation without getting answers in between. You could go from, if you wanted to, obviously here to here and to here. So you just want to kind of do it all in one calculation, set up with dimensional analysis. You could go all the way to the end without getting answers in between. If you want to get answers in between, like normal, you want to kind of avoid a lot of rounding until kind of the end and stuff like that. Any questions on that? That's what I did at the end here. Yeah. So we have normal, we just kind of multiplied here and divided whatever was on the bottom. Yeah. Yeah. Yeah, so it's a very good question, and it's a question people really screw up with a lot with stoichiometry, which is remember that when you're doing molar mass and you're calculating molar mass, it is based only on the formula. So for any of these guys here, if you had to do the molar mass, it should only be done. This is how many grams there is per 1 mole, which assumes 1 mole is just the formula by itself. You don't want to do it there and then do it here with the stoichiometry at the bottom. You're going to be in trouble, right? So 100%, that's a very common error people make. You want to do molar mass just from the formula regardless. If the coefficient in front of the equation is like 42, just do it based on the formula always. And that's really, again, what the definition of molar mass is. Other questions? All right, we're laid up there for